Look, the Earth is breathing. The Earth's crust, the surface on which we all live, and its atmosphere are in constant communication. Every year, the crust breathes out CO2 and methane into the atmosphere, greenhouse gases, from its lakes, its forests, its soils. In the same places, and often at the same time, the Earth is also breathing in, absorbing those gases and synthesizing new life from them, which we generally call organic matter. Now, the Earth is breathing and changing on a global scale, and this influences our climate. But its lungs are smaller than the tip of a tack. They're microbes. By definition, forms of life that are invisible to the naked eye. Despite their size, the sheer amount of microbes on the Earth makes them the most biologically important force on the planet. As an example, bacteria are the most abundant life forms beyond plants. As an example, again, in soils, pick up a teaspoon anywhere you like. In that teaspoon, there's 1 billion microbial cells representing thousands of species. It's for this reason that soil microbes release 10 times as much CO2 to the atmosphere every year as human fossil fuel emissions. Microbes have been keeping our planet habitable silently for millions of years, even though we consider them in contexts like disease and germs. But right now, we're in a time of unprecedented change. Human-induced climate change is reshaping environments at a pace that we can't keep up with. Despite this whiplash in the environment, microbes continue to breathe CO2 in and breathe it out. The rhythm of life continues. What we'd love to understand is how that rhythm will change in the coming decades due to climate change. But you can't study microbes the way you might study a forest or an ocean where you can count trees and fish. We can't count cells at that magnitude. So when something evades our physical observation, we turn to chemistry. In my thesis, I developed chemical tools called stable isotopes as a way of probing microbial activity in the environment. What I've found is that these tools can tell us whether systems are breathing in or breathing out, and how quickly they're breathing. Specifically, I looked at the continental subsurface where the majority of bacteria live, and I found that these environments kilometers below our feet are slowly breathing out CO2. And if this can be extrapolated all over the world, it could be important for climate change. When we want to understand the Earth's breath, we need to look at its lungs. Turns out, you just need a microscope.